welcome back. Today's lesson, linear approximations and differentials. It turns out that you have been sheltered in your math life, most likely, and that lots of things in math we don't get nice, beautiful, exact answers for, or we can't know, or they just take too much time. And so a good approximation method ends up being really important. Also, theoretically, it's good to have approximation methods so that we can simplify hard abstract problems into ones that we can really work with. So let's start right with something that is tangible and understandable. If you wanted to estimate the square root of 102, just ballpark it, don't touch a calculator, what would be a good guess? What about is the square root of 102? And then when you're done with that, maybe just take a good guess on what you think roughly the square root of 98 is. Ballpark it. And then let's think about how you came up with that. So I'm hoping that when you said the square root of 102, that's pretty darn close to the square root of 100. It's a little bit bigger than the square root of 100, and the square root of 100 is 10. So this should be 10 and change, 10 and a little bit, whereas the square root of 98 should be a little bit less than 10 because it's a bit less than 100. So I don't know, maybe the square root of 102 is like 10.1, something like this. Similarly, we could look at something like sine of 0.05 and say, oh, that's pretty close to sine of 0. That's a 0. Sine is increasing, so I don't know. Maybe it's like about 0.04. It's something slightly bigger than 0. The question we might ask ourselves is, great, we could pick a nice number to sort of anchor ourselves at and then say move up or move down, but how much should we move up or move down? How fast is it growing at that point? And if I say it like that, I hope you realize how fast is it growing at that point? That is a good question for derivatives. So let's just back up a little bit. Historically, tangent lines were just approximations. And this is more than historically. This is now too. So what I've done is I've graphed the same thing 4 times, and I've just zoomed in. So here's e to the x. Notice how fast it grows when we actually graph it. And here is x. So this is the tangent line to e to the x at 0. And it's roughly got, right? It's got that same rate of change at 0. It's doing what it's supposed to. But otherwise, it just looks like this thing attached to the edge here. But as I zoom in more and more, what you notice as I get closer and closer is that those two curves start looking more and more alike. And so one of the ways you could approach from the very beginning calculus and derivatives is to say, oh yeah, I want the line that looks like my curve if I zoom in enough. And in some ways that's what a limit is doing, right? It's staying really, really close. So a tangent line is just the line that looks like your curve when you zoom in further and further and further, right? As I zoom in, that curvature starts to look flatter and flatter because I'm getting less of it. And it starts to look more and more linear. So locally, most curves look like their tangent line. And locally just means in a small area, right? Very, very close. So we're gonna treat a tangent line this way, not as the rate of change per se, but as an approximation to my curve. Say, okay, as long as I stay really close to this base point, my tangent line is a good approximation of my curve itself, of those y values themselves. So let's see how we could actually do this using our example, the square root of 102. So, well, I probably need a function here. That function is going to be, looks like f of x equals the square root of x. Great. I would like a base point to find my tangent line that's going to give me a good approximation to 102, and we decided that 102 is pretty close to 100, and 100 is a great number to plug in. Okay. We're also going to need a derivative, of course, this calculus. So the derivative of x is 1 over 2 square root of x. And so I'm going to need 2 more values here. I'm going to need f of a is equal to 10. The square root of 100 is 10. And I need f prime of a the square root of the derivative when I plug in 100 is going to be, looks like 1 over 2 times 10 is 20. Great. Okay, so I need those numbers, but if you're not sure why, you'll see in a second. My tangent line, let's see, if I use my point slope form, looks a little bit like this, where I plug in my x and my y value. So my x value is 100. My y value is that f of a, so my y value is 10. Okay, just plugging in that 100 into f. And then I multiply it by the derivative for my slope, and that slope is 1 over 20. Look at me, I found the tangent line. At x equals 100. Okay, great, using that point slope form. In fact, if I really wanted to, and let's go ahead and do that this time, I could bring over the 10, and I'm going to write it a little bit funny. Y equals 10 plus 1 over 20, x minus 100. All right. I know a lot of you are used to seeing the b at the end, but I'm going to write it like this for my own secret reasons that you'll see. So now that I have an equation for the tangent line, I would like to use that tangent line to basically approximate some number, that's not where it's touching, but a little bit off where it's touching. And that should give me a pretty good guess of what the y value is, because at least at that point, it is growing at the same rate. So it gives me a good sense of how much I should increase if I step over a bit. So let's go ahead and plug in here. Let's plug in 102. That's the x value we care about, and we get y equals 10, the y value we started with, plus, how fast I'm growing at that point, that slope at that point. I plug in 102 minus 100. Okay. Notice, by the way, that this 102 minus 100, that's how much my x value changed, right? I'm going up by 2, and then I'm just multiplying by my rate of change. So I'm starting at 10, I'm stepping over by 2 to the right, and then this tells me if I step over by 2, how much is my y value going to increase? And this is just, looks like 10 plus 2 times 1 over 20 is 1/10 equals 10.1. Oh, look at that. Did I do that right? 2 over 20 is 1/10. Oh, that's beautiful. 10.1 on the nose. So that is our approximation of the square root of 102. And it's a pretty darn good one, actually. I encourage you right now to plug square root of 102 in your calculator, and you should see that you get something just a wee bit bigger than 10.1. I know that, side note here, I know that because I know that a square root kind of has this sort of a curvature to it, and I know that my tangent line is going to be sitting on top. It's that concavity. And so it's going to be a little bit above the actual estimate. Okay. Or it'll be a little bit above the true value. Okay. So basically, my y value changed by 0.1 along this tangent line as I move to the right. Brilliant. Not so bad. Maybe we should formalize this. Maybe I should actually try to give this some words and a formula in there too. So a tangent line approximation at x equals a, sometimes it's called based at x equals a, is called a linear approximation at or based at a. So if you're using a tangent line, sometimes people will just say a tangent line approximation, but linear approximation, we're approximating with a line. So bit of terminology there, gets used a lot. And so if we wanted to use a linear approximation based at 100 to estimate the square root of 102, well, that's just what we just did, right? We'd say, oh yeah, and I'm going to go ahead and peek ahead a little bit. I'm going to say this linear approximation, let's call it L of x. L for linearization. L of x is going to be equal to 10 plus 1 over 20 times x minus 100. So this is my new approximation function using a line based at x equals 100. So L of 102, we just said was 10.1. Boom. Ta-da! Nice. Good job. Let's keep going. We're on a roll here. So the function for the tangent line is called the linearization based at a. And we'll often just say the linearization. And that's what we found. That's why I wrote it as this L of x. Okay. This is math. We should be able to do this without a particular function in mind. We should be able to figure out a formula for this linearization, L of x, without saying, hey, find the tangent line and kind of solve and do some stuff. Let's see if we can do that process of finding the tangent line and solving for y, but let's do it in the abstract. So let's go ahead and give myself just a little space over here. So I've got some function f, and that function f has a derivative. Okay, and I think we said before we need an a, and we're going to need an f of a, which is that y value, and we need an f prime of a. Okay, this is all we really used before. So now if I want my tangent line, I can actually give you a formula for it. Well, my point slope form says it's y minus stuff equals that slope times x minus my x value. So what's my x value? Well, it's just a. What's my y value at a? Well, it's just f of a. Whatever that value is. And then I need a derivative, and that derivative is just f prime of a. So don't be confused. A is a constant, and so this is a constant, this is a constant, and this is a constant. So I've got y minus some number, which is the y value of my point, equals the slope that I want, which is the derivative, some number, times x minus a, that the x value we're based at. Great. We're almost there. All we got to do is solve for that y, and we get y equals f of a, because I added it to the other side, plus f prime of a times x minus a. That's it. That's the y value of my tangent line. Let's go ahead and write that right over here. L of x is just going to be, same thing, f of a plus f prime of a times x minus a. Okay, this can feel like a weird thing to memorize or learn, but I hope if you understand what these parts mean, it's pretty easy to remember. My approximation for my y value, this L of x, this linear function, is just what's the y value I'm starting at, f of a, plus how far to the right I go, times my slope. So if I go this far to the right, I need to multiply by my slope to get the change in y. So this whole term over here is the change in my y value along that tangent line. Amazing. All right, with this newfound power, we should be able to do a couple of these. So let's do this one more time, just for habits. Square root of x based at 100. Let's find that linearization for repetition's sake. So f of x, we've seen this before, is equal to the square root of x. F prime of x is equal to 1 over 2 root x. A is equal to 100. F of a is equal to 10. F prime of a is equal to 1/20th. And now if I really want to, I can plug this into this formula above. I don't like talking about plugging things into formulas. I hope these formulas aren't just memorized, but they're speaking to you about content. So we're starting at this y value, f of a, plus my derivative is the slope, or that rate of change, times how much my x value is changing. X minus a is 100. Boom. Ta-da. But that formula, if you do memorize it, it can make your life a little bit faster. There's no reason why you couldn't actually figure this out just by solving for a tangent line on the fly every time. And frankly, if I ever forget this, I just remember, oh yeah, it's a tangent line, and I solve for y in that tangent line. Okay, nice job. Okay, let's do one more. Sine of 0.05. Here we go. We're going to go, we need an f. Well, what function? Sometimes you got to choose. Sometimes you actually have a little bit of freedom, but this one I think is pretty clear. Sine of x. Some people will do things like sine of x plus 2, or some little adjustment to make their life easier later. So don't be shocked if you see that. The derivative of sine, cosine of x, at what x value? Well, here you got to be smart. What would be a good x value to choose? We want something close to 0.05, but also something that is easy to plug into sine. So I'm going to choose 0. Makes sense. Sine of 0, I know what that is. By the way, what is sine of 0? That's just 0. What is cosine of 0? Well, that's just 1. So my linearization for sine of x is just, well, I'm starting at 0 plus my slope is a 1 times x minus 0. Oh my gosh, do you see what this is? Yeah, it turns out sine of x basically looks like x near 0. If we were to graph this real quick, there's my attempt at sine of x. Here's my attempt at x. And you see that as you go through 0, they're looking pretty much the same. This is an amazing fact, and this gets used by physicists a lot, actually, that for small angles, you can just kind of replace your sines with x's, and you get a pretty good approximation. This is also maybe worth pointing out that, as a side note here, we had this limit as theta goes to 0 of sine of theta over theta, and we said that is a 1. And one way you could argue why this is true is because near 0, sine theta is acting like theta. Right? Near 0, it is well approximated by theta. So this ends up looking like this. And there is a whole approach to calculus and limits that focuses very much on, hey, let's replace functions with their linear approximations in limits and use those instead. We'll see this a bit when we do L'Hopital's rule a bit later as well. So, fun fact, nice to keep in mind that sine of x is basically just x near 0. Okay. One more for the books, maybe 2 more. I just like them too much. Let's approximate the natural log of, how about, let's do 0.9. Why not? We'll do a couple of 0.9s. So if I wanted to estimate the natural log of 0.9, play the same game. My function, you don't have to do all of this if you don't want to. You can jump in a little further, but it's worth at least writing down that derivative. The derivative of natural log, 1 over x. Nice job. What a am I going to choose? Definitely write down, where am I going to base this at? So I need a number close to 0.9 that is also nice in the natural log. How about 1? I think it's a good choice. Why is that a good choice? It's close to 0.9, but also, what is the natural log of 1? That's a 0. That's super nice. What is the f prime of 1? So 1 over 1 is just a 1. Oh my goodness. Do you see what's coming? This looks a whole heck of a lot like what was happening before. Let's give this a try. We got our L of x is equal to, well, the y value I'm starting at, so that's just a 0, plus my derivative is a 1 times x, and now minus my a value is a 1. So this is just x minus 1. Nice. Oh my gosh, we didn't quite finish our last problem either. We still got to plug in. So let's plug in this one and we'll go back to the one above. Sorry about that. L of 0.9, I really should plug in, is just 0.9 minus 1 is equal to negative 0.1. Perfect. And that makes sense. We should be a bit below 0 if we're a bit below 1. Let's finish off this one from above. Ooh. L of 0.05 is just 0.05. It was a little too obvious. I forgot to actually write it down, but I should write that down. Okay. Yeah, very good, reasonable estimates. And there's really no limit to how or the power that you're doing this, other than your ability to sort of also estimate the errors that you might have. Okay, last one on this video, and then we'll do something else with this. Let's go ahead and estimate inverse tangent of 0.9. Whew. Looks like it could be scary, but fear not. Trust the method. Well, I know my function. That's going to be inverse tangent. I know its derivative. Do you know its derivative? It's definitely the most important inverse trig derivative. 1 over 1 plus x squared. That's a good one to keep in your back pocket. My a, so I want an a value that is close to 0.9 and also plays nice with inverse tangent. So I'm going to go ahead and say 1 again. Why? Because f of 1, inverse tangent of 1. What is inverse tangent of 1? Where is the tangent equal to 1? Okay, it might help. It might help if I remind you that tangent gives the slope, right? Because it's sine over cosine, so it's rise over run. So where is the slope, say on a unit circle, going to be 1? Our old friend pi over 4. Yep, that's that 45-degree angle. That's when the slope is a 1. And then I got f prime of 1 is going to be, looks like 1 over 1 plus 1 is 1/2. So not so bad. There's a pi in there. L of x is equal to, well, the y value I start out, so pi over 4, plus my slope is a 1/2 times x minus that a value I'm starting at is a 1. And I just got to plug in L of 0.9 is pi over 4 plus 1/2 0.9 minus 1 is pi over 4. And then this is negative 0.1. Half of negative 0.1 is minus 0.05. I'm going to leave it like that on these approximations. Yeah, go ahead and plug in your calculator, give a decimal to a few digits out. If we're doing an approximation anyway, it makes some sense to give a decimal formulation, but I'm going to leave that nice and exact like this. Okay, that's it for this video. Next up, we'll get even more abstract and talk about differentials. My last little nudge here is, hey, I know there's a formula and people like formulas and plugging in, but make sure it makes sense, that underneath it's just a tangent line, and you know how to find a tangent line. And if you totally forgot this formula, you could still find the linearization by just solving for y in that tangent line. All right, see y'all next time.